Hello, my name is David, and in this video I want to show you something that is not easy to explain, and actually you need to be already a pilot that knows about the polar curve of a glider and your glide ratio. First thing that needs to be clear is that the maximum speed of a glider with hands up normally, let's say 38 kilometers per hour. So at 38 kilometers per hour, if I find headwind, wind coming, which is 38 kilometers as well, my ground motion is zero. I'm gonna be sinking down. The wind, the headwind, equals my airspeed, my motion. So I sink down. On that scenario, obviously, it is very interesting to push your speed bar. You go full speed, but you can increase your speed from 38 to 55, and that is the way that you're gonna penetrate into the headwind. Clear. What about in zero wind? In zero wind, no wind, and I'm flying nicely at trim speed 38 kilometers per hour. So at 38 kilometers per hour, if I want to reach farther away, if I want to cross that hill or that little village or that forestry, I shouldn't touch. I shouldn't push full speed bar, because then when you push full speed bar, you change the angle of your glider, and actually the performance of your glider it's penalized big time. So in zero wind, if you want to reach further, you don't touch, you don't go full speed bar. But in 38 kilometers headwind, obviously, if you want to go farther, then you push your speed bar. Where's the point? At what speed is the equilibrium in between? You know, where should I start pressing my speed bar? On an ENA glider, on school gliders, that is one of the gliders that most used in the world of paragliding, paramotoring, schools, recreational beginner pilots, and accuracy pilots. It's been a question rolling around the accuracy pilots for the last year. Should I push the speed bar or not in order to reach farther when a little bit of wind is coming? And actually, it's quite surprising to put the data of a polar curve into a graphic and compare your trajectories in different winds. And this is what we're going to do. We're going to ask the polar curve to give us that information, and we're going to draw in a graphic the trajectory in between two different scenarios: pushing full speed or not pushing full speed. So in order to make this, we found a file that the Swedish Aeronautical Institute, something like that, asked. It's going to be here. Ask BGD. So BGD made a file of 20 pages, something like that. Pretty thick. I mean, a lot of formulas, physics, aerodynamics, complex. But we get to the page number 12, where we find a couple of graphics that we should know what it means, and it's the glide ratio and the polar curve. We're gonna fix on the polar curve, because polar curves talks about the sink rate at different speeds. So sink rate is meters per second, and speed it's also meters per second. So they both can be translated on a diagram where x and y it's going to be meters on the surface, and height. So let's get into it, and let's make this comparison. It's going to be surprising. All right, so we're going to take the green line out of this graphic, which is the ENA gliders. And you can see that the line, the curve goes all the way down to 55, down says 55 kilometers per hour. That's the maximum speed that we're going to take as a reference. And at that speed, we have minus 3 meters per second of sink rate. And the other point of reference that we're going to have is 40 kilometers per hour, which is just a little bit, 1 or 2 kilometers ahead above trim speed. All right, so what do we have here? We have a graphic, and down here we have 0, 5, 10, 15, 20, 25, 30. This is the ground. And here we have 5, 10. This is our height. All right, so these lines will be the trajectory of our flight. So in point A is the beginning of the trajectory from a paraglider. Point A is a paraglider that comes flying from here. So we are going to have two different scenarios at two different speeds, 55 and 40, but both flying into headwind, which is 20 kilometers per hour. So at 40, we have a sink rate of 1.6, and at 55 we have a sink rate of 3 meters. So we're gonna check how is it gonna behave the glide. Okay, so first scenario, it's gonna be 40 kilometers per hour airspeed minus 20 kilometers headwind is 20 kilometers per hour ground speed, which is 20 kilometers per hour is 20,000 meters per 300, 600 seconds. So in 5 seconds, we will have that we advance 27.7 meters. So from point A at 40 kilometers per hour airspeed, we are gonna arrive to, in 5 seconds, to 27.7, and we are gonna be sinking at 1.6 meters per second. We're gonna be sinking in 5 seconds, 8 meters. So we sink 8 meters here and we advance 27.7. So that's the trajectory that we're gonna draw in between A and B for the speed of 40 kilometers airspeed. All right, so at the speed of 55 kilometers per hour minus 20 is 35 kilometers per hour ground speed, which is 35,000 per 3,600 seconds. So in 5 seconds, we made it to 48.6 meters. But we sank down 3 meters per second per 5, it's 15 meters sank. So from 16 we sank to 1 meter, and we went forward 48. So we went to point D. So the line in between A and D, when you touch the ground, it's around 3 or 4 meters shorter. So the conclusion of this graphic is that pushing the speed bar all the way down in a scenario of 20 kilometers per hour headwind, it is not interesting in order to reach farther. If you want to reach farther, you shouldn't go full speed. You should better go 40 kilometers per hour, which is a little bit over 38 kilometers per hour, which is trim speed. All right. Okay, now we have a different scenario. Now we have 25 kilometers per hour headwind, and the calculation goes that at 25 kilometers per hour, our ground speed at 40 kilometers airspeed comes down to 15. So we are only going to make in 5 seconds 20.8 meters and still sinking the same 8 meters. So this is point B, all right, and point C will be at 41.6. So actually point C a little bit further. At 25 kilometers per hour headwind, now it is interesting to push full speed bar, because the trajectory from A to C, it goes farther away than the trajectory from point A to point B. All right. So 25, it is the wind that on an ENA glider you should be pushing full speed bar in order to reach farther away. Yeah, it might be surprising, the results of these calculations, but this is not a theory. This is just translating all the data from a polar curve into a graphic where it shows the trajectory, differences in trajectories in different winds. So in the world of accuracy, it will be surprising for many people. This obviously does not apply the same in other gliders. Actually, you have the curve lines, the polar curves of different category gliders, and each category glider you can make your own calculation. All right, I hope it helps someone around.